Hi, I am Jonathan, the Mix Helper. Welcome to my channel. And today I want to speak about EQing and more specifically about what should we do with the fundamental frequency when we are EQing. So a few weeks ago, I posted a question in a poll in a few Facebook groups, and here's the question I asked. When we're EQing a channel, and in order to enhance the character of the instrument that's recorded in this channel, should we enhance the fundamental frequencies of that instrument? Over 200 people responded and answered the poll. And as you can see, the vast majority of them said that the answer is no. In fact, in one of the groups, 100% of the participants answered that the answer is no. In the video today, I'd like to dive into the subject, look at what are the fundamental frequencies and what are the rest of the frequencies that present when an instrument plays a note, compare them, and answer the question in a more scientific way. So for the purpose of the analysis today, let's look at a couple of instruments. We'll start with an oboe, and we're going to look at what happens when we play the note A1, which has a fundamental frequency or a pitch at 110 hertz. So as we can see, the lowest frequency that's present in the spectrum is indeed the 110 hertz, which is the root or the first harmonic or the fundamental frequency. And that is the pitch of the note that we're playing. However, if we look at the spectrum, we see that there are many, many other frequencies present. We call them harmonics. And if the first one was the first harmonic, now we're looking at the second, third, fourth, and so on until we get to the nth harmonic. And it's very easy to calculate what is the frequency of these harmonics. If the first harmonic is 110, the second one will be 220, the third will be 330, and so on and so forth. And the frequency of the nth harmonic is going to be n times the fundamental, in this case, n times 110. If we further subdivide these frequencies into groups, we can speak about frequencies that create the tone of the instrument, sometimes called overtones, and some of them create the timbre of the instrument. And in some texts, they are referred to as resonant frequencies of the instrument. Now, it might be a little misleading because some texts, especially modern ones, refer to more than one fundamental, and then they are called fundamentals, and the rest of the frequencies are called partials. I am not going to use these terms in today's presentation because they're a little bit misleading. So in today's presentation, we're going to simply speak about a fundamental frequency and harmonic frequencies. And we're going to speak about them differently and see how they contribute to what we hear. Let's now compare the same oboe playing two notes. First, we look at the same one, the A1 at 110 hertz, and then we will look at A2 at 220 hertz. So the fundamental frequencies correspond to the pitch. And we can see on the left the A1 with a fundamental at 110, and on the right we can see the A2 with a fundamental at 220 hertz. But what happens with the rest of the harmonics? Let's draw a line that connects the tips of each one of these harmonic frequencies. This line is now creating what's called an envelope that has a shape that's very particular to this note. Let's do the same with the A2 note that has a fundamental frequency at 220 hertz. Now let's remove the background and focus only on these two envelope lines. Let's enlarge them and overlap them. We can see that even though they start from a different fundamental frequency, they actually correspond quite well with each other, which means that the envelope is not so dependent on the pitch, even though we started with two different pitches. One is the A1 at 110, and the other is the A2 at 220. The envelope of the harmonic frequencies actually looks very much the same. Let's do something else now. Let's look at the same pitch played by two different instruments. And in this case, we're looking at the oboe playing A2 at 220 hertz, the same one as before. But now we're comparing it to a clarinet playing the same note at the same pitch, A2 at 220 hertz. And I'd like to repeat the same analysis that we did before. So on the left, we can see the clarinet playing an A2 at 220 hertz, and we can see the fundamental frequency at 220 hertz. On the right, we can see the oboe playing A2 with a fundamental frequency of 220 hertz. Now let's create the envelope again by connecting the tips of the harmonic frequencies. So on the right, we have the oboe, and we'll do the same on the left with the clarinet. Let's remove the backgrounds, enlarge these two envelopes, and overlap them. Now we can see that even though the two instruments are playing the same pitch and have the same fundamental frequencies, the envelopes actually look very different from each other. So to summarize, two different instruments playing the same pitch, which is what we see on the left, create very different envelopes, while the same instrument playing different pitches create envelopes which look very much the same. And that's what we can see on the right side. This actually makes a lot of sense because our experience tells us that an oboe playing different notes still sounds like an oboe, while a clarinet playing different notes still sounds like a clarinet. But if we compare a clarinet and an oboe playing the same note, they do sound different. Now, if we look at the fundamental frequency of these two instruments playing the same note, A2 at 220 hertz, and if we compare the spectrum of these two and we look only at the fundamental frequency, they look pretty much the same. Now, if we EQ and enhance only the fundamental frequencies of these two instruments, are we enhancing something that they have in common or something that differentiates between the two? In other words, if we want to enhance the character, which is the difference between these two instruments, is enhancing the fundamental frequency going to help us? Or maybe if we enhance the harmonic frequencies of the two instruments, we enhance something that differentiates between the two and therefore enhance the different character of each one of these instruments. I think that the answer to this question should be already apparent. So after reviewing the theory, let's test this in practice. So I have an oboe playing an A2. Let's listen to it. And I have a clarinet playing A2. Let's listen to it. Also, let's look at the spectrum. So here's the oboe. And here's the clarinet. And you could see that in both cases, the fundamental was at 220, like the theory says. Now let's look at EQing so that we can only hear the fundamental. So as you can see, I did something very, very extreme here. That's the oboe EQ and that's the clarinet EQ. So I really cut everything below and everything above the fundamental and enhanced the fundamental. And I did the same in both cases. And let's listen to how this sounds like. So I turn them on. And let's listen to the oboe. And to the clarinet. Can we hear any difference between them? The answer is not really. Let's do it again. So when we only listen to the fundamental, all we hear is one fundamental frequency, and there's not really any difference between the two instruments. Now let's see what happens when we're not completely cutting the harmonics and enhancing the fundamental, but just relatively. So in this case, we are enhancing the fundamental by a little bit on both instruments and cutting a lot of the harmonics on both instruments, but they're still present. Let's hear how this sounds like. So here's the oboe, and here's the clarinet. So in this case, we start to hear some difference between them, but this difference is really small. And if we look at the spectrum, here's the oboe. So we still see harmonics and a fundamental. And here's the clarinet with its fundamental and its harmonics. And you can see that they look different, but since we've cut a lot of the harmonics and enhanced the fundamental, they sound pretty much the same. Now let's do the opposite. Cut the fundamental on both instruments and enhance the harmonics on both instruments. And let's listen to how this sounds like, and also look at it at the analyzer. Here's the oboe, and here's the clarinet. Oboe, clarinet. So in this case, we actually enhance something that's different between them and cut everything that's common between them, or as common as possible between them. So the result is a larger difference between the tones of these two instruments. And I remind you, those two instruments are playing the exact same pitch, A2. Now let's put this to a test and listen to what happens when the two instruments are playing together. And in order to demonstrate this, I recorded a simple melody in two voices. The oboe is playing one voice, the clarinet is playing a different voice. And let's only listen to the fundamentals and hear how the two voices sound together. So we can definitely hear both voices. However, they don't sound very different from each other, so they blend and they mask each other. And it's very difficult to distinguish between the two voices of this melody. Let's now listen to what happens when we do the second type of enhancement. So we cut a lot of the harmonics and we enhance the fundamental, but we still keep some of the harmonics in the game. So that's definitely better. We can now hear better separation and less masking between the two voices. Now let's listen to what happens when we do the third type of EQing that we demonstrated before. So I remind you, this means that we're cutting almost all the fundamental and we're enhancing the harmonics. And let's listen to how this sounds. So it is very obvious that when we do this, we actually create the best separation between the two instruments. And that's also very logical and very easy to understand, because we're cutting away everything that's common between them and that sounds absolutely the same, which is the fundamental frequency. And we're enhancing whatever sounds different between the oboe and the clarinet. And when we do this, it actually creates the best unmasking between the two voices of this melody, because each instrument now has a different range or different area in the frequency spectrum where its character is most enhanced and different compared to the other instrument. So let's repeat this. Here's the melody with the best separation. And here's the melody with the worst separation. So hopefully I was able to convince you with a live demonstration that the theory actually works. And when we want to create separation between two instruments, we should try to enhance whatever is different between them, which are the harmonics, rather than trying to enhance the fundamental, which is actually what's common between them. Thank you very much for watching, and stay tuned for the next videos.